potassium hydroxide and some phosphoric acid here. In order to get this done, you had to use some of both. They came to you in a burette, so we're going to start by making a little data table here so that we can keep track of how much of each we're going to use. Give yourself about 3 lines up here at the top because we're going to put some stuff in there later. And our key players here are going to be, we'll go this direction, some H3PO4 and some KOH. They're going to come in burettes. So we're going to do this from the perspective of an initial burette reading, a final burette reading, and an amount used. So I'm going to go over here to my burettes and go after my initial readings. Remembering that our burettes are marked off to the nearest tenth of a milliliter, means I can read to the nearest hundredth of a milliliter. H3PO4 starts out at 25.49 milliliters. And my potassium hydroxide .94. So there's my start point. A lot of you had figured out that the key to doing this had something to do with trying to mix the potassium hydroxide and the phosphoric acid in exactly the right ratio to get them to kind of use one another up completely. Some of you approached this from kind of a guess and check standpoint, like let's mix 5 milliliters of each, and then once we've mixed 5 milliliters of each, let's use the phenolphthalein to check to see, do I have leftover acid, do I have leftover base? Okay, if I have leftover base at that point, let's try it again, using a little bit more acid and a little less base. Use the phenolphthalein to check it, and that is definitely a valid thought process. It's kind of slow, it's tedious, but it will definitely get you there if you're just using the phenolphthalein to try to figure out what's the exact ratio to use these up. The other possibility is to use the phenolphthalein to sort of keep track of, in the moment, am I acidic or basic? Because the phenolphthalein will change color as the acidicness or basicness of the solution changes. That's the slightly more efficient way to accomplish exactly the same thing. You're still trying to figure out what ratio it takes between the two of them, but you're doing so in such a way that you don't have to do one, check it, do one, check it, and just constantly keep adjusting it. Most people who do this for the first time decide that they're going to start with the potassium hydroxide, use the phenolphthalein to make it pink, and then add the acid until it's not pink anymore. And that that's going to be kind of the point at which these two things exist in the perfect ratio. It's slightly better to do this, however, in the other direction, only from the perspective of it is much easier for the human eye to detect when a color appears for the first time than when the exact moment at which the color finally disappears. So if you went from the pink to clear, you certainly did just fine. That's where most people start. However, you'll get slightly better results if you go the other direction. And that's the direction we're going to go. I'm going to start by putting some phosphoric acid in my flask. And I'm going to take quite a bit, like like a little over 10 milliliters, so that I've got 4 significant figures on my volume. The other advantage to taking quite a bit of this is that if you end up off by a little tiny bit in the very end, a little tiny bit of 10 milliliters is a much smaller percent error than a little tiny bit of, say, 1 milliliter. So I've got some phosphoric acid in my flask. I'm going to add my drop of phenolphthalein. Stays clear, which we totally expect because this is acidic. Now I'm going to take the potassium hydroxide and I'm going to add potassium hydroxide until this turns just the very, very, very palest amount of pink. That's going to be hard to see against the black background of my table, so I'm going to use a white piece of paper to help me out here so that I can see a little better when it turns pink. My paper there, open up the potassium hydroxide, and for a while I can let this run pretty quick. I'm going to start to see hints of pink appearing when I get close. And that's when I'm going to know I need to slow down this operation a little bit. Now at this point, I'm going to do a little rinsing of the walls with some deionized water, because stuff has been splashing up on the wall. I want to make sure that all of the acid and base are down here where they can mix together. It doesn't matter if I add a little extra deionized water because I'm measuring everything coming out of the burettes. So having some extra water in there doesn't impact anything at all. And now because it's starting to stay a little pinker with every addition, I'm going to slow this process down so that the burette is adding 1 drop at a time. I'm looking for the point that I can go from pale pink, or from clear to pale pink, with just 1 drop of the potassium hydroxide. And I need that pale pink to hang around for about 30 seconds to a minute before it fades away. Every drop here, it's staying pink just a little bit longer. I might be getting there. Since I think I'm getting close, I'm going to do another rinse. Make sure I have everything down in the flask. And again, trying for 1 drop at a time here. Not quite there yet. Still clear. That'll probably do it. There we go. Very, very, very pale pink. I went from clear to pale pink in 1 drop. The pale pink color is hanging around long enough for us to kind of talk about that pale pink color. And because it's pale pink, I know that I have achieved this is ever so slightly basic. Okay? I'm actually beyond the point of them being exactly used up and exactly equal to one another, but I'm 1 drop past that point. You know from drops on a penny that there's about 20 drops in a milliliter. I am about 1/20th of a milliliter over the line. That's not really a huge percentage when you consider that I started with 10 milliliters, a little more than 10 milliliters of acid, and I've used a whole bunch of base. And that's part of the advantage to using a slightly larger number, is that one drop it takes to turn it color is a much smaller percentage over the overall total here. Okay, so we've achieved having it be basic. Now we need to take our final burette readings. So 36.34 on the phosphoric acid. And 42.70 for the potassium hydroxide. Okay, for our amounts used here, we just have to do a little subtraction. .85 milliliters of the phosphoric acid. .76 milliliters of the potassium hydroxide. Okay, good to go there. So just to kind of think about small victories here, how many of you in some way, whether it was like this or some other way, tried to get these two things to equal one another out and figure out how much of each it took? How many of you got that far in the thought process? Good. Okay, so that's a major victory, to realize that what we're doing here is trying to get them to even one another out. The next part then is what am I going to do with that information? And knowing what to do with that information is important as well. Now, this little process is called titration. So we're going to go back and label the top of our paper. That's the word for what I just did. Titration is the process of reacting two solutions until both reactants are exactly used up. It's most commonly done with acids and bases because you have to have a way to know when you've hit the point of exactly used up. And with acids and bases, we can use phenolphthalein. We can watch for that turning pink situation, and then we know we've exactly used up both of them. The next step is knowing what to do once you've got these two volumes. So now we're going to start plugging our way through some calculations. So the nature of the problem here is that we had to find the molarity of the H3PO4. That's the thing that earns cupcakes, knowing what the concentration is on the H3PO4. In order to do that, we have to think about how these two substances interact with one another. I'm going to intentionally leave a blank line here, and we're going to do our equation down one line. We have H3PO4, which is aqueous, reacting with potassium hydroxide, which is aqueous. And you were told in your information about this process that this is a double replacement reaction. So we have to think about what we're going to get for products. H3PO4 consists of hydrogen ions and phosphate ions. Potassium hydroxide consists of potassium ions and hydroxide ions. And our double replacement says everybody has to trade partners. Once we trade partners, we got to write good chemical formulas. So the potassium's going to get together with the phosphate, but it has to do so as K3PO4. I'm going to assume that's aqueous, just because if it had been solid, there would be something cloudy or chunkier, and there would be something in my beaker to indicate that was a solid, so we're going to assume it's aqueous. And hydrogen gets together with hydroxide in a 1-to-1 ratio. What's HOH? Water, or H2O. And we'll change that in a second once we get this thing balanced. It's a little easier to balance it if we think of it as HOH than if we think of it as H2O. So if what I'm really trying to do is neutralize this or make water, every 3 hydrogens is going to take 3 hydroxides to use them up and make 3 water molecules. And so now that we've got it balanced, we'll change this to be H2O. So after getting them to react in exactly equal amounts, the next important thing is to take into account that they react in a 1-to-3 ratio. That for every 3 KOH particles you put in, there was 1 H3PO4 in there to start with. So you had to know that you had a 3-to-1 ratio. Now we're going to set ourselves up with an IBCA table to make use of that 3-to-1 ratio. I'm going to leave 2 lines for my information row, because I've got a couple things I want to put there. And then we need our before. I always do 2 rows on my change and my after. Here's my I row. Before, double tall on my change, and my after. The reason I wanted to make my information row double tall is I wanted to put the volumes of each of these into here. So the H3PO4, that went with the 10.85 milliliters. And the potassium hydroxide with the 18.76 milliliters. One of the things that can go wrong here in making these titration calculations, it's really easy to screw up which volume goes with which substance. So if you just add an extra row to your I row, that can help you out. As part of your packet, you were told that you had 0.175 molar KOH. That was information given to you in your packet. That means for the potassium hydroxide, I know that every liter of this contains 0.175 moles of KOH. My problem is that I don't know how many moles are contained in a liter of phosphoric acid. And that's ultimately what I'm trying to figure out here, is how many moles per liter on that. But I do know something here about where I'm starting. I know that I used 18.76 milliliters of KOH. I know that there are 1,000 milliliters in a liter, and that every 1 liter of this potassium hydroxide contains 0.175 moles of the potassium hydroxide. So I can figure out how many moles of potassium hydroxide I used. 18.76 divided by 1,000 multiplied by 0.175. 4 significant figures, unlimited significant figures. 3 significant figures, I get to keep 3 in my answer. 0.00328. And that's moles of potassium hydroxide. So I know how much potassium hydroxide was used in the reaction. The other most important thing that makes titration special is to understand that we did this until we had nothing left of either reactant. That was the whole purpose of the phenolphthalein, was to run the reaction until both of these went to 0. When we do titration problems, we're going to kind of work through our BCA table in the shape of a U. We're going to start with what we know. We're going to work down. We're going to hop to the other reactant, and then we're going to work our way back up. So titration problems generally happen in the shape of a U. If I start with 0.00328 moles of the potassium hydroxide, and I use it all up, that must mean I spend 0.00328 moles. And now I have none left. In order to spend this much potassium hydroxide, I also have to spend some phosphoric acid, but I only spend 1/3 as much. .00328 divided by 3. So I spent 0.00109 moles of the phosphoric acid. And if I stopped the reaction when I went to 0, that must mean I started with 0.00109 moles of phosphoric acid. Now I just need the molarity. Molarity is number of moles per liter. I know what volume I used. I just need to put that into liters. So I used 10.85 liters. Oh, milliliters, sorry. There are 1,000 milliliters in a liter. 0.01085 liters. And then I have to calculate my molarity, which is the number of moles of phosphoric acid I used, 0.00109 moles of H3PO4 in 0.01085 liters H3PO4. Turns out this stuff was 0.100 molar H3PO4. answers that I received.